right, so we'll get started. Welcome everyone to the second Q&A session for the final exam for COS 217. I guess before we plunge into specific questions on material, are there general questions about the exam itself, the format, about what's on it, anything along those lines? All right, so I guess we'll see everybody bright and early tomorrow morning, 9 a.m. on Gradescope. I promised to go over a couple of specific previous exams. Obviously, can't sort of walk through all of the picky little details, but we'll try to touch on the major points of the questions. So we're going to start with spring 2019. So I will go ahead and share that. All right, so this is a question that is fundamentally about recognizing a performance bug and trying to figure out kind of where it happens, why it happens, what can be done about it. Can the compiler help you out? So the basic question is looking at a very simple function that is going to do some manipulations on a string. And it's asking if the code is compiled without optimization, what is the running time of string fill as a function of the length of the string that is passed to it? And so, you look at the code, you see that, here is a loop. You ask how many times is the loop going to get executed? Well, it's once per character in the string, so it gets executed n times. And what does the loop do? What happens within the loop? Well, something pretty simple, just a single assignment. But then the real key to this was recognizing that another thing that gets executed every single time through the loop is this increment, and that's no big deal, but then also this comparison. And the comparison calls string length, and of course in C, the only way to find out the length of a string is to actually walk down the string looking for the null byte. And so each call to string length itself takes some amount of time that is proportional to n. And so we have something that takes time proportional to n. It gets executed n times. The overall running time is proportional to n squared. And this is one of the real classic performance bugs that you encounter when you're dealing with strings in C. So the second part of this then asks you to write a optimized version of string fill with a lower order dependence on n. In other words, it can't be proportional to n squared anymore. It has to have some lower order dependency on n. So what can we do? Well, there's not much we can do about kind of doing this assignment. Right? This assignment kind of we're going to have to do anyway. And so really the way to do this is to focus on not calling string length a whole bunch of times. And the reason you can get away with doing that is because string length is always going to return the same value. And how do you know that string length is going to always return the same value? Well, it's because of the nature of how you're modifying the string. If you weren't modifying the string at all, then it would be pretty obvious that string length is always going to return the same value. But if you're modifying the string, then, there's some tiny chance that you might have modified the string in a way that changes the length of the string. But because we're saying we're replacing characters in the string with some character C which must not be null, we know that we can pull out the string length out of that loop. And so you would wind up with code that basically pre-computes the length of the string and then uses that constant in the comparison. And so the final part of this question was, could a compiler actually do this for you? And the answer is no, because of the thing that I just mentioned, which is The ability to do this transformation relies on the fact that the length of the string isn't going to change as you go through this loop. And that's really only true because this character C must not be null. And because there's nothing in the code that verifies that C is not null, the compiler has no way of reading this comment and doing this transformation, because the compiler is really only going to do transformations that it can prove to itself aren't going to change the meaning of the code. And so that was kind of the point here. The transformation is equivalent only if C is not null. If C is null, the null byte \0, then the compiler can't really do anything. Okay, any questions on that? All right. Let's move on to question 2 on this exam. Is not something, it relates to an assignment that we had in previous versions of 2.17, not this semester, so it wouldn't really be fair to ask you about heap managers. So instead, we're going to talk about assembly language. So this question basically says, translate this assembly function into idiomatic C and write a comment saying what the function does. So let's, plunge on into this and try to understand what this function is doing. So we recognize the first line here as just standard part of our standard prologue. We're allocating a stack frame that is 16 bytes long. We're putting the return address of the function in the first part of that stack. And then we are taking x0 and putting it on the stack as well. So we remember that, parameter passing conventions in AR64, the first parameter goes in x0 or w0, depending on what the size of that is. So just by looking at these first 3 instructions, we know that we're going to have a function, and the function is going to be taking 1 parameter. So we can already kind of go and we're going to say, we're going to have some function called mystery, and it's going to have, some parameter, and we don't know the type of that parameter yet. Okay, so here's our function. That's what we know so far. So now we go back to our function and see what else we're doing. The next thing we're going to do is take that first parameter, which we just stored on the stack, and load it into x1. And then we're going to take our, that value, and we're going to sort of use it as a pointer. We're going to take the thing that is located wherever x1 points, that is, wherever that first parameter pointed, and we're going to load that into w2. And we notice that this is an LDRB instruction. So this is a load byte instruction. So whatever the thing is that was pointed to by that first parameter, we are dereferencing that pointer and we are loading a byte into W2. So, all right, that gives us a lot of clues about what the type of that first parameter had to be. We know that it had to be a char star. All right, now we're going to compare that thing that we just loaded to 0. And if it is equal to 0, we branch to the very end. And at the very end, we are loading the saved return address. We are fudging the stack pointer to deallocate this stack frame, and we're calling return. Now, you notice that as part of this sequence, we didn't really do anything to, explicitly store a return address in x0 or w0, which is where it naturally would go. So we've gotten kind of 2 pieces of information from this past bit of analysis. One is that we don't think we have a return from this function. We don't think we're returning anything. And the second is we have compared the thing that we loaded, from the result of dereferencing that pointer to 0, and if we found 0, we are returning right away. So at this point, we can sort of go back into this function, and we can start, filling in a few more details. One thing we're going to do is we're going to say that this function is void, so it doesn't return anything. And the next thing we're going to do is, this parameter, we are dereferencing, we're checking for the null byte, so probably we're thinking of this parameter as a string. That is, we're interpreting this not just as a pointer to a character, but probably we're going to be thinking of this as a string of characters. So I'm going to go ahead and rename this to S, and I'm going to write kind of this statement that says if star S equals, the null byte, we're going to go ahead and return. Okay, back to the code. We've so far kind of made it down to here. And now it's the next thing we're going to do. We're going to add 1 to the value of whatever was in x1. That was our pointer to a character, this thing that we've been calling s. So we're adding 1 to that, storing it in x0, and doing a branch and link back to mystery. We're doing a function call of mystery. So this is in fact a recursive call because we're calling the same function that we're in. And we set up something to go into x0, namely 1 more than s, this parameter that we got in. And so these two lines basically constitute a recursive call to mystery where we're passing in 1 more than the parameter we got in on this invocation of mystery. So this is kind of this call to mystery of s plus 1. And again, it's a void function. It doesn't return anything. And so we don't need to assign its return value to anything here. All right, what else are we doing? Well, we got back from this function call eventually at some point. Now we are reloading our parameter, this thing that was, offset of 8 from SP. That was just as. We're reloading that into x1. We're re-dereferencing that pointer. So W0 gets star S. And we're calling toUpper. So toUpper is this function that takes a character and returns the uppercase version of it. And what is the parameter that toUpper took? Well, it's whatever wound up in W0, which is just star S. So somewhere here, we're going to now have a call to toUpper of star S. But now toUpper, we know that that does return a value. And so we need to sort of figure out what we're doing with that value. Well, so here we have yet another reload from the stack of S. And now we are storing a byte from W0, which was the return value of toUpper, into the thing pointed to by S. So basically this bit of code translates to star S gets the return value of toUpper called on that character. Okay, and now we go into this epilogue where we're going to clean stuff up and return. So this is basically it for what the code is doing. But now we were asked to write a function level comment kind of explaining what the code is. So now we need to decipher what all of this nonsense is doing. Well, somehow it is converting characters to uppercase, but it's doing so in kind of a weird roundabout way. In particular, it is sort of doing this recursive call to convert the rest of the string, not including the first character, to uppercase, and then it is converting that first character to uppercase. So that's the algorithm, but what is the function doing? It's basically, replace string pointed to by s with uppercase version. So something like that. Okay, so hopefully that's walking through the thought process of how you would interpret a function like this, and we're going to see maybe another example of that in one of the other problems we look at today. Okay, so you can kind of compare this to the answer key, and hopefully I got it right. So this is a slightly different way of writing this. Basically, it's saying that if star s is not equal to 0, we're going to do all of this stuff, as opposed to if star s is the null byte, we return, otherwise we do all of this other stuff. So even a fairly straightforward bit of assembly language, there might be different ways of having it correspond to assembly language code. Actually, this would probably be a little more literally representing the way we asked you to translate code to assembly language, but there are lots of different ways of lots of different pieces of C code that correspond to a given piece of assembly language. Quick question, how did you figure out what the return type was, or when to add in a return statement when you were looking at the assembly code? So kind of the giveaway there is to see how, intentional the code is about storing something in either x0 or w0. In this case, the giveaway is really that the code isn't doing anything special about setting x0 or w0 to be a return address that we that means something. It's just, whatever happened to be there. If you see code that in all the paths that lead to a return statement, it is setting up, it is being intentional about what it does with setting x0, then you know that there is some sort of return from the function, and then you have to figure out is it x0, is it w0, and you have to figure out, what was that value that got stored there doing in the code? Was it behaving like an int? Was it behaving like a long? Was it behaving like a pointer? Was it behaving like a char or something like that? So if we go to the L0 statement at the first compare, don't we already have a value at x0? Namely, isn't that where the initial function input parameter was stored? So yes, absolutely. So one of the little ambiguities in assembly language is that, well, something has to end up in x0. And so that's why I use this word intentional. Does it look like the code cared about what wound up in x0, or was it just kind of doing its own business and whatever wound up there, wound up there? And I agree that it's not always, completely obvious as to whether a given assembly language function is intending to return a value or not. And this really is one of the things that you lose when you go from a high-level language like C, where you have to express your intentions. about types, about return values, and about parameters, as opposed to assembly language, where just kind of whatever happens in the code happens. You, as an assembly language programmer, don't have to declare your intentions that we're returning a value of some particular type or not. So that's what makes deciphering assembly language, a little bit tricky, and it does require you to kind of look at the little clues that are scattered around the code. A small follow-up. How does the machine then know not to return that initial function input parameter at x0? Well, as far as the machine is concerned, there's no such thing as, taking parameters, returning parameters. This is all done by convention. As far as the machine is concerned, there's a value in some register. How you as the programmer choose to interpret that value depends on the conventions that you're using. And for functions that different assembly language programmers write to be interoperable with each other and to be interoperable with the C compiler, you do have to adhere to certain conventions. So could you write mystery in assembly language like this and in C code call it and expect a parameter? Yes. Would that parameter make sense in the context of this code? Not really. So that's what I mean about declaring your intentions versus just having the code do something that happens to agree with the conventions about how we use assembly language in a particular programming environment and on a particular operating system. Okay, so hopefully that it's hard to kind of convey this philosophy of programming in assembly language, but you really have to get into the mindset of the code is what it is, the values in the register are just numbers, and whether you interpret that number as an int or as a pointer really depends on conventions and really depends on how is that acting in the context of the particular code that you're executing. All right, now the other part of this was to, write an assembly language function that does the same thing, but doesn't use recursion and uses callee saved registers. So for this, I'm actually going to, switch to the, answer key and just sort of go over the code that was provided here. So one difference that you notice is that obviously there are no recursive calls. We're not calling mystery. We are doing the same thing with a loop inside the code. Right? So there's going to be this loop that starts here. There's a branch back to the beginning of the loop here, and we're just, executing something over and over again until we branch out of the loop with this comparison. So whenever you are writing, assembly language code, it's always nice to, sketch out the algorithm, whether it's in C or whether it's in pseudocode. So, here's basically what we want to implement in assembly language. You'll notice that we are using the callee saved register x19, and that is going to hold the parameter that we passed in. So throughout this entire execution, x19 is going to hold the value of this pointer s. So now here we have our loop. We load a byte that x19 points to. We compare it to 0. If it is 0, we branch out of the loop. Otherwise, that character, that char, is now sitting in W0, perfectly ready to be passed to 2 upper. The result of 2 upper gets stored back in whatever s points to, and we increment s and go back to the beginning of the loop. The only difference in the epilogue of the function is that we now have to restore the callee saved register that we as the callee saved at the very beginning. Okay, so any questions on this? All right, let us now move on to Fall 20, which is the other exam that I promised to go through. So you'll notice that this was a different style of exam than previous COS 217 exams, and in fact it's different from what we're doing this semester. This was intended to be an open book exam, and so there are some questions on this exam that I don't think would be fair game to ask you this year, basically because you don't have access to man pages and the textbook and other reference material. So one of those questions is in fact about Bash and about shell programming and a variety of different shell utilities. So, we'll go over this very briefly, but realize that these are not the types of questions that would necessarily be fair game for this year. So the first question was, which of these produces an empty file, assuming that my file does not already exist? Here we are calling the echo command. Now, echo takes its parameters, it prints those parameters to standard out, and then it prints a new line. And so if you call echo without parameters, it's going to print nothing, and then it's going to print a new line. And so my file does not wind up as an empty file. The command touch, if a file doesn't exist already, it creates it as an empty file. If it does exist, it just updates its time step. We kind of briefly mentioned this when we were talking about make. At any rate, touch on an empty file touch on a non-existent file does indeed create an empty file. The colon command is another command that does nothing. And so if you redirect its output to a file, you get an empty file. This is one of these questions about short circuit evaluation. There were some questions on Ed about kind of the AND version of this. This is the OR version of this. And the thing to realize with this double ampersand or the double vertical bar is that these are short circuit operations, both in C and in Bash. And so if you can evaluate the first thing and already know what the result of the AND or of the OR is going to be, you don't bother executing the second thing. So true or anything is guaranteed to be true. And the command true does indeed set its return value to 0, indicating that it succeeded. So something that is logically true or anything is going to be true, and so the second part is not executed. And this would be true if this were a C function call, and it is true even if it is a command on a Bash command line or in a Bash script. And so this second part is not in fact executed, and you do not create an empty file. Here there is an explicit kind of null command. There is nothing, and it is redirected to my file using one of these special redirection operators. It's not one of the usual ones, but it is, very related to, the redirection operators that we have talked about, and in fact, it will create an empty my file. So those were kind of the basic Bash questions. Part 2 of this is you have two programs, first and second. You would like to execute first, and then execute second only if first succeeds. So what are some ways of actually writing that? Well, so here is the one that involves the short circuit evaluation of the AND flavor. Basically, if first does not succeed, if it is logically false, then you already know how the AND is going to turn out. And so you know that false and anything is false, and so you don't bother executing the second command. This is maybe a more conventional way of writing it with an if-else. Basically, if first, then second. Phi is how you end the if in bash. And then here is you first just execute the first command, and then you explicitly check its result code, its return value. And this $question mark is a special shell variable that contains the, what the previously executed command returns. And we're saying that if that is equal to 0, 0 indicating success, then we execute second. And if it is anything non-zero, then obviously we don't execute second. Okay, the next question is about, workflow optimization, optimizing you, the programmer, basically. And it's asking if you have a bunch of commands you're going to be using over and over, how do you improve this workflow? And if there's one thing we wanted to convey to you in COS 217, improve your workflow, automate the process of building, debugging, testing, executing commands, make very heavy use of things like bash scripts, make files, maybe other things like bash aliases, or you could actually, even if you're going to be lazy and not create a bash script for it, at least don't retype the, 50-character command. At least try to, find it in the bash history and reuse it from there. So, I don't know whether to say don't be lazy and write the bash script or be lazy and write the bash script. But this is like really one of the things we want to convey to you in COS 217 that will serve you very, very well in really anything that you do going forward. Think about scripting, think about automating everything you possibly can. All right, any questions so far? All right, building and testing. Here we have a piece of code. There are, kind of different code paths through it. The one kind of tricky thing that you have to recognize in this bit of code is that we have a switch statement, and one of our favorite good, bad, misguided, who knows? One of our favorite features of switch statements in C is that unless you write break, they're just going to keep on going. And so if x equals 1, it'll execute this code, then it'll execute this code, then it'll execute this code, then it'll execute this code, and then this code. It'll execute everything in there because there are no breaks in there. And so once you recognize that, the answers to these questions are fairly straightforward. How many data sets in order to achieve complete statement testing? Well, if you want to execute every single statement in here, just pass in 1 for x. You'll go through everything in this switch statement. On the other hand, in this if-else statement, there is no value of z you can pass that will execute both this and this. And so how many different runs through the code will you need in order to achieve complete statement coverage? Well, you need 2 runs, one with x equal to 1 and z equal to, anything true-like, anything non-zero. So that'll get you all of this stuff and this line. And then the other data set is anything you want for X, and then 0 for Z. So that'll get you that executed. How many data sets for complete path testing? Well, for path, you have to kind of look at all possible combinations. So for the switch, you want to run through the whole thing. Then you want to run through just starting at case 2, and then you want to run just, through the default. For the if, you want to run through this part of the if and that part of the if. So you have 3 ways of going through this, 2 ways of going through that. So you need 6 data sets to get complete path testing. Create a proper makefile for the dependency graph below. Okay, so we have a target executable. The target depends on 3 .c files, and the C files have various dependencies on .h files. So first question, how many rules, how many line target dependency command sets of lines in the makefile are you going to need? Well, at a minimum, you're going to need to be able to build the executable, and for all of these .c files, you're going to need to convert them to .o files. So if you structure your makefile properly, you can get away with 4. 1 to build the executable, and 1 to build each of the .o files from the corresponding .c file. And now, what are the things that those depend on? The executable should depend on the .o files, period. The executable should not depend on .c files, should not depend on .h files, should not depend on the phase of the moon, no funny business. It should depend on .o files, that's it. The rule for a .o file is that it should depend on one .c file, and then whatever .h files might affect whether or not you need to rebuild that C file. So if this .c file includes this .h file, and that .h file includes that other .h file, then if you change this .h file, that might affect what happens in this .c file. So the rule for a .c file, for a .o file, is the one .c and all .h's. And so if we look at this makefile that was created here, we see the executable depending on .os. We see each .o depending on a single .c, and whatever .h files are sort of in the tree or in the graph of dependencies that those .c's might possibly depend on. Other things you could do, you could obviously switch up the order, but if the target doesn't go first, then you'll need kind of all : and the the actual executable name going first, so that you have a sensible default thing if you just type make. Okay, so any questions on that? All right, next. This question 4, is going to be all about understanding where strings and other forms of data live in memory and how long they stick around for, and just really making sure you're solid on those rules of scope, of scope, visibility, and duration. All right, so here we have a bunch of code snippets, and we're asking which ones result in the stack section containing 6 bytes of the string stack. So the stack section is where local variables go. So we know that unless we have a local variable that is kind of big enough to hold those 6 bytes, they can't go on the stack. They'll have to go somewhere else. So let's look at the first one. Here we have an array of char, and we are specifying initial values for the different bytes in that char array. So is it a local variable? Yes, in fact, it is a locally allocated array of characters. And it is initialized with the particular values containing 6 bytes of the string stack. And so A kind of fulfills the conditions that we had. B, here we have a local variable, but the local variable is not an array of char. It is a pointer to char. And where does it point to? Well, this constant string got stuck way off somewhere in the RO data section. So what is on the stack? Well, it's not those characters of that string. It is a pointer to somewhere off in RO data. So this does not fulfill the conditions we wanted. And now here we have a char array that is locally allocated locally. It's a local variable. It's on the stack. And we're going to call strcopy. We're going to call strcopy from a bunch of characters that live way off somewhere in RO data into this location that is, in fact, on the stack. And so what we wind up with is, after the execution of this strcopy, the characters stack null were not on the stack to begin with, but they got copied in there. And so after the execution of this, we're totally fine, and we have the string stack being located on the stack. Questions here?
Is there a difference between using the bracket notation or using the asterisk to denote just like the string pointer or a char pointer? So like, for example, in let's say in part C, instead of like using the bracket 6, if we just did char asterisk stack, like would that still work?
That would not, in fact, work. Why? Because you have now allocated on the stack some space for a char pointer. You did not say what that char pointer was going to be pointing to, so it is pointing way off to, Neverland. Luck of the draw would happen to be on the stack. And then if you call strcopy in the same way you have it here, well, wherever that char pointer happened to be pointing to, who knows, you would try to copy these characters there. So this is one of these situations where a pointer to a character and the name of a character array very much do not behave the same way. There's some situations where you can interchangeably use a char pointer and the name of a character array, but when it comes to figuring out where stuff is allocated, how it's initialized, how long it persists, what you're allowed to do with it, you do need to keep in mind that difference between a character array, which might in fact live on the stack, or it might live somewhere else in memory, and a mere character pointer.
I'll note that it makes a big difference. If you look at A versus B, these, if you have this misconception of array pointer duality being they're always the same all the time, you would think, oh yeah, that effectively does the same thing. But because of this nature that the actual the letters S, T, A, C, and K in the null byte live in the stack versus in RO data, it changes what you can do. In A, you could do stack of 0 gets some other character. In B, if you did stack of 0 get some other character, it doesn't work because you're attempting to edit something in RO data, and RO is of course read-only.
And that's really kind of the point of this series of questions, this entire question 4. It's to really force you to come to grips with all of these subtle differences. For example, the difference between this and this. Okay. Would C work if stack were initialized as a pointer and then malloced before the string copy? Yes, that would work. Because now, well, it would work in the sense that you wouldn't be copying into, somewhere random, but malloc, remember, allocates memory on the heap, not the stack. So different part of memory. The pointer itself lives on the stack. The data the pointer is pointing to lives in the heap. Okay. All right. Speaking of heap, the next sub-question is all about heap. Following code snippets, which snippets result in heap being located in heap? So here we are mallocing, some memory. That memory is in fact on the heap. The heap pointer itself, like we said, is on the stack. That's fine. And now we're trying to do this assignment. No, wrong language. That doesn't work in C. Basically, this is in fact a pointer into RO data somewhere, and all we're doing here is we're adjusting this heap pointer to not point to this malloced memory anymore. It is now pointing to wherever this constant string is in RO data. And so not illegal, but it does not result in the string heap, winding up on the heap. Here we're allocating some memory on the heap. Remember, calloc also works on the heap in addition to malloc. Here we have a pointer to something in RO data containing the string heap. And now we are doing a string copy the long way, kind of character by character with a for loop, instead of doing something sensible like calling a string copy. One thing you'll notice is the limits of this for loop. We're only copying 4 bytes from pile to heap. Now, is this a problem? Well, if this were just a malloc, it would be a problem, because that 5th character could be, who knows? But calloc, remember, one of the differences between calloc and malloc is that calloc initializes memory to 0. So even though we didn't explicitly copy the terminating null byte, it was already a terminating null byte. We just didn't bother to change it to anything else. So after executing this bit of code, we do in fact wind up with the string heap on the heap. F. Here we are allocating a pointer to a char. Okay, so a location that contains a pointer that points somewhere else. And now we're setting that pointer to be something. This is the kind of question where, without having access to a man page, we maybe wouldn't expect you to know exactly what strcpy returns. In fact, strcpy does return a copy of the, the string that got copied. But it turns out you don't even need to know that to answer this question. Because as soon as you malloced some memory, and string copied heap into that memory, heap wound up on the heap. And so all of this stuff outside of it, as long as it doesn't crash, which in fact this doesn't crash, is kind of window dressing. The important part is this strcpy. As soon as that executes, you get the string heap located on the heap. So questions on that? All right, next we have data. So this one here we have, notice this is declared outside of a function. So this is in fact a global variable that's an array of char, and we stuck the letters data in, in that globally allocated char array. So if this were within a function, that would wind up on the stack. But if it's outside a function, then it does in fact wind up in data. This particular case, here we have a global pointer, but then we are assigning that pointer to point to a constant string, and that's in RO data, not in data. Here we have a pointer, and it's a global pointer to data. And we, it currently points to this string. That is, again, a constant string. That string is in RO data. So the data pointer itself is in data, but the thing it points to is in RO data. And again, just as we saw kind of 2 questions ago, we're just fudging this pointer to now point somewhere else. But the somewhere else that it points to, unfortunately, still is a constant string and therefore in RO data. And finally, let's do the BSS version. So here we have a pointer. The pointer is global and uninitialized. So the pointer lives in BSS. But just as in so many of the questions before, the thing that it points to is in RO data, not in BSS. Here we have an array in BSS, and then we copy some characters into it. So that, in fact, does work. And here we have a pointer that we have initialized to null. And we're trying to copy something into whatever null points to, and you get a nice big fat splat, the program segfaults. Questions on that? Why is it that in G, data is not in RO data? Okay, so here, we are initializing the value of an array. So it's very clear if we have kind of this syntax where we're initializing it one character at a time. Here, we are using a shortcut provided by the C compiler. So whenever you see an array of char being initialized, in your mind, you need to translate this to this kind of syntax. Because if it were an array of anything other than char, if it were an array of ints, this is the syntax you would have to use to initialize the elements of that array. This is the one kind of shortcut the compiler gives you, but in fact, you are initializing an array as opposed to causing a pointer to point to a constant string in RO data. So there's so many of these subtle distinctions, especially when we're dealing with strings like this. And being really, really clear about all of these different distinctions is something that we do want you to, get your head around, really pay attention to all of these subtle distinctions.
In G, won't there also be a copy of DATA null byte in RO data?
Depends on the compiler. I think most compilers won't, in this case, bother to allocate another copy in RO data. There might be some compilers that do.
So I just happened to have run it to answer an ed question, and in this case, it is not in RO data. It literally just has the machine instructions of a sturby of the ASCII code, but it would not be a completely unreasonable thing for the compiler to generate it as put this string in RO data and then do a bunch of sturbies from RO data. That's load LDRBs and sturbies.
or even a stir copy or something like that.
All of the above, yes.
Mhm.
Yeah, I have a quick question about H and I here. So just to understand, I know they're not, they don't do the desired like execution in this case, but so like H here, like you're initializing like a string in the BSS section, right? Because like we're not giving an explicit value, and then when you like in the second line, that's saying like it's pointing to a string in RO data. Is that correct? And then in I, um, it's the same thing except because we give it an explicit value, it's set into the data section first, but it's also pointing to an RO data literal. Is that correct?
What you said was almost completely correct. The one thing that, the one kind of picky little thing for H, you don't have a string in BSS. You have a char pointer that lives in BSS. And similarly in I, you have a char pointer that lives in data, pointing to something in RO data. Whenever you have pointers, always think about this distinction about the pointer versus the thing pointed to. They can very well be in different locations in memory.
Okay, I see. That helps. And then I guess just to clarify the distinction between like the pointer and the bracket notation, you're emphasizing how like when we use the bracket notation like that, we should just think of it as like on the stack or
So
like
when you use, so, this, there are two different things. One is where the variable is, whether it's on the stack or in data or whatever. And the other one is what does it mean to initialize it and what is it initialized with? If you're declaring an array, regardless of whether it is an array on the stack or in data, when you initialize it, the compiler literally copies characters into, onto the stack, or sets up the data section so that the right characters wind up in the right locations in memory. Whereas when you're talking about a pointer, you have the pointer itself that lives somewhere, and it ends up pointing to some other location, which can very well be RO data in the case of constant strings.
okay, that makes sense. Thanks.
All right. It is 3 o'clock. Unfortunately, at this point, I have another meeting that I need to run to, so I am going to